Welcome. In this video, we won't try to teach the full formalism of special relativity. Instead, we will ask a much simpler and a deeper question. What was Einstein's problem? What exactly was bothering him about the physics of his time? And how did that lead to the birth of special relativity? Just as Newton's orbit problem pushed the development of calculus, Einstein's own relativity problem pushed him to rethink space and time themselves. In this video, I am not going to rush into the Lorentz transformation, time dilation, length contraction, and so on. This video is about Einstein's problem, which ideas in physics refused to fit together in a comfortable way. What made him feel that something in our concept of space and time was not quite right. You can think of it in parallel with the earlier video, Newton's orbit problem and the birth of calculus. There, a single sharp question forced the development of new mathematical tool. Here, several threads come together to form Einstein's relativity problem. In a way, Einstein's problem was, you can say, much involved. By the end, I want the same questions that disturbed Einstein to be alive in your own mind. Only then are we really ready for the technical part of special relativity. Around 1905, Einstein was working as a patent clerk in Bern, but his real work was thinking very hard about physics. On paper, everything looked impressive. Newtonian mechanics described the motion of planets, projectiles, machines with great success. Maxwell's electrodynamics described electricity, magnetism, and light, unifying them into one theory. But when he tried to hold both theories together, we will see how, and apply them to moving bodies, he saw certain tensions. He noticed strange asymmetries in the way electrodynamics was described and very unclear role of something called an absolute rest frame or ether. And now many people might have said the equations work. Why worry? Einstein did the opposite. He took these tensions very personally. You can summarize his attitude in a sentence like this. If two theoretical descriptions of the same experiment look very different, perhaps our concepts of space and time are not yet right. So today we will unpack what that means. The famous magnet conductor example that Einstein uses in his 1905 famous paper is not the only seed from which spatial relativity grew. There were several important ingredients. Experiments like Michelson-Morley, which tried and failed to detect Earth's motion through a hypothetical light carrying medium. They used to call it as ether. A growing clash between the way velocities add in Newtonian mechanics and the idea that the speed of light is this small c should be the same for all observers. And confusion, often not fully acknowledged, but what it really means to say that two distinct events happen at the same time and how we synchronize clocks. Hmm? Taken one by one, each of these might have been ignored or patched. Taken together, they pushed Einstein to a more radical conclusion. Perhaps we need to think space and time themselves, right? Let's start with the example Einstein himself chooses at the beginning of his 1905 paper, a magnet and a conductor. Imagine a magnet and a piece of conducting wire arranged so that if some relative motion between them, a current flows in a conductor. Very simple. Experimentally, what we observe is simple. The current depends only on the relative motion between the magnet and the conductor. If the magnet moves, the conductor is at rest. We see a certain current. If conductor moves and magnet is at rest, with exactly the same relative speed, we see a current of the same strength along with the same path. So far, so good. Now look at the theoretical description in the standard Maxwellian language. Here an asymmetry appears, and this is what bothered Einstein. You see, it was this asymmetry in the Maxwellian language. That's the main point here. Okay, we go ahead. In the first case, when the magnet moves and conductor rests, the usual description says changing magnetic field gives rise to electric field in surrounding space. That electric field has a certain energy density. Where the conductor passes through this region, the electric field drives the current. In a second case, when the magnet is at rest and conductor moves, the usual description says there is no electric field in space near the magnet. Instead, charges in the moving conductor feel an electromotive force simply because they are moving through the magnetic field. This EMF produces a current with the same path and the same intensity as before. So physically, the two situations are indistinguishable. The current is same, the heating in the wire is the same, everything observable is the same. The theoretical stories that we tell is different. In one case, we talk about electric field in space carrying energy. In other, we call mysterious EMF in the conductor with no corresponding field energy in space. Einstein's reaction was the phenomenon only depends on the relative motion. So why does our theory care so much about which object we choose to call moving and which we choose to call rest? This is the first hint that our framework may not be optimally chosen. We now turn to a different thread, the luminous or a luminiferous ether. In 19th century, light was understood as a wave. Wave usually need a medium. Water, water waves, sound waves, air, I mean sound waves travel in air, so forth and so on. So many physicists assume there must be a medium filling all of a space which carries light waves. Huh? And this was luminiferous ether. If Earth moves through this ether, there should be an ether wind, somewhat like airflow for airplane, light traveling along or you know, against uh, this ether wind should have a slightly different speed, like relative to Earth. So these are the parallel things. Experiments like Michelson and Morley were designed with a great care to detect this drift. Essentially, to see light's speed depends on the direction of Earth's motion through the ether. Again and again, the result was null. Within experimental accuracy, you can say there was no such effect. This suggested something quite radical. You see, these radical things only have given birth. right from the Copernicus. Uh, anyways, so this radical is perhaps the phenomena of electrodynamics and optics do not reveal any property that corresponds to the idea of an absolute rest frame. Yeah, perhaps there is no ether wind, nothing. Not because of our experimental weakness, but because the concept is not needed at all. So this is the radical thinking. And you see, now everything follows. So let us recall how velocities add in everyday mechanics. This is very simple. There is you can say a train 10 meter per second, and then you throw a ball 5 meter per second relative to train. These are very simple things. Essentially, observer on the ground says that the ball is moving 15 meter per second, so forth and so on. So this is a Galilean velocity addition, and it works. I mean, very well for all these ordinary speeds. Now, suppose we try to apply the same idea to the light. Now, if a source of light moves at a speed v relative to u, and if emit, obviously the speed is c relative to itself, and now if you apply the Galilean rule that in your frame the light should move perhaps at the c plus minus p, yes, or minus plus p. But Maxwellian's equations, that is the fundamental equations of electromagnetism, contains a speed small c which appears as true constant of the theory. It has it is just a mathematical output of those equations, and it was because of mathematical output simply a constant. And experiments suggest that observers in very different states of motions still measure the same numerical value. As I said, it is a mathematical output of a certain equations, vector equations. Uh, see, Uh, and so therefore this C should be same regardless of motion of the source or whatever. So we now have a clash. Simply Galilean relativity says velocities add, whereas electromagnetism suggests that the speed of light is same for all inertial observers, right? All frames. Both principles are beautiful on their own. Together in their naive classical form, they cannot both be true. See, something deeper must change, deeper, something deeper. And this is where the beauty of the great mind, perhaps. So, a more subtle but equally important thread concerns the idea of time and simultaneity. See, time is very simple concept, but you see, it is deep at the same time. In everyday speech, we say things like two events happened at the same time, even if those events are far apart in space. But if you think in operational terms, this raises a sharp question. How do we actually decide that the two distant events are simultaneous? See, if you have a clock next to event A and a clock next to event B, you must have some procedure to synchronize this clock, right? Typically, such a procedure uses signals traveling from one place to another. Einstein pointed out that if we are serious, we must base our definition of simultaneity on such operational procedures, on exchanging signals. And in practice, those signals are light signals, but obvious. Once you define simultaneity using light, you immediately involve, C, small c. and that is finite. And your definition becomes sensitive to the state of motion of the observer. In other words, the old idea of single universal time ticking the same way everywhere for all observers start to look too naive. See, because of this small c angle. This is the conceptual root of spatial relativity, time, and therefore simultaneity are not as simple as they first appear. If you pinpoint the constancy of c, because the c is the secret of the signal. See, and c is constant, and this was the same thing with the gravitational force. See, it was instantaneous, and this also disturbed many people. And this simultaneous C is also instantaneous. Mm. And C is not infinite. So this disturbed Einstein as well. Anyways, let's now bring together two of these threads, magnet conductor example and the ether experiments. Uh, From the examples like the magnet and the conductor, from the repeated failure to detect this Earth's motion through the ether, Einstein drew an important conclusion. The phenomena of mechanics and electrodynamics show no sign of any special absolute state of rest. Nothing in the observed behavior of electric and magnetic field or of the mechanical system signals out a preferred inertial frame. Because any inertial frame, the, the fact, the observed effect is the same. In fact, as had already been shown approximately, the same laws of electrodynamics and optics appear to hold in all frames in which Newton's equation of mechanics are valid. Einstein proposed to elevate this observation to a principle, and that is named as principle of relativity. At this point, Einstein makes two bold moves. He promotes two ideas to the status of postulates: principle of relativity, the law of physics, mechanics, electrodynamics, optics are the same in all inertial frame. No inertial frame is a spatial. Hmm? Very obvious. And the constancy of the speed of light. Light in empty space propagates with a definite speed, small c, which does not depend on the motion of the source. Taken one by one, each postulate is reasonable and both have a strong experimental support. But if you combine them with the traditional Galilean way of thinking about space and time, they seem to be incompatible. This is what I am calling Einstein's relativity problem. How can we define space, time, and motion in such a way that both principle of relativity and constancy of speed of light are true? The answer will require new kinematics, new rules for relating the space and time coordinates used by the different inertial observers. Einstein's new viewpoint has some striking consequences for the old ideas. It does not require an absolutely stationary space with the spatial properties. There is no need to imagine a physical ether filling all of the space with respect to with which everything else moves. Nor does it assign a velocity to the points in empty space. Instead, it focuses on the relationship between uh, rigid bodies and the coordinate systems, we, clocks with the time uh, at different locations, and the signals. that move between them. So these are the three things. He emphasizes that many of the difficulties encountered by this electrodynamics of so-called moving bodies came from not paying, you say, attention to this uh, questions, kinematical questions. So, in a way, you say, how do we define a distance? See, now this is fundamental questions now pop up. If you try to correlate these things, it directly hit the very core. Again, then how do we define time? See, how do we compare measurements in different inertial frames? These are the questions. So, spatial relativity is, you can say, at its very heart, a new way of answering these questions. No, questions in the kinematics. So let us collect these threads we have been following. The magnet conductor example, it's an asymmetry in the theoretical Maxwellian language. Phenomena themselves only depend on the relative motion. That's the core of this thread. Ether drift experiments like Michelson-Morley, they failed to detect any relative motion, suggesting that the absolute rest may not be meaningful, or it may not be simply there. And the Galilean velocity addition, which clashes with the constancy of the sea. So that means our notions of time and simultaneity, these are we will say naive notions, uh, will be unclear and tied to how we synchronize clocks, right? Because ultimately it's the light signals that is the base of synchronization. Okay. Together, this forms Einstein's relativity problem, we can say. First is, how can all inertial frames be truly equivalent? How can the speed of light be same in all of them? How can we do this without invoking an ether or an absolute rest frame? What changes must we make to our core concept of space and time? If we have done our job well so far, certain questions should now feel natural to you. If the physical currents in the magnet and this conductor depends only on the relative motion, why should our description, the theoretical one, care so much about which object we call at rest? Huh? We have seen this as case 1, case 2. Now, if experiments is cannot find the ether, does it still make sense to talk about absolute state of rest? Huh? It is this. I mean, now we can say, is it possible to keep both a relativity principle saying all inertial frames are equivalent and a universal light speed small c without changing our understanding of space and time both together? No. And what does it really mean to say that two distant events are simultaneous? How would we test that with real clocks and signals? These are the questions that led Einstein to special relativity. In the next videos, we will follow how he answers them by redefining simultaneity, by introducing new transformation laws between inertial frames, and by accepting that the time and length themselves are relative. Spatial relativity is not just a collection of formulas. It is response to a very specific problem, the one we have tried to reconstruct here.